Hello everyone, welcome to the channel. I hope you all are doing great. So in the last class we started with the new series that was the previous year questions of the CSIR NET exam, and in that the first chapter that we have started was the kinetics. So some of the year's questions we discussed in the last part. Now this video is gonna be the part number 2. So if you have not watched the previous part of this playlist I have made on the channel, you can check that, or I'll provide the link to that in the description. Even from that you can get the access. Okay, so let us begin with the part number 2 now. Before starting the video, if you are coming to the channel for the first time, make sure you subscribe to the channel and to hit the like button also for the video if you understand the concepts, and share it with your friends as well. Okay, so let us begin with this one. So this one first question. So this question we did in the last class, last part also. So there I thought that some of the data it is missing, but in actual we missed one of the thing over here. So this was from the CSIR June exam conducted in the year 2011. So the question it says is, observe the following aqueous solution of the same compound. This thing I missed over there. All the measurements are made at the same wavelength and at the same temperature condition. The solution A that you are having, so three of the solutions A, B and C were given to us. We were to compare their optical densities, which means their absorbance value we had to compare it. Okay, so the first solution we are having is the transmittance of this much concentration solution using the 1 centimeter length, it is 0.5, which means transmittance value it is 0.5. We know that absorbance is equal to the negative log of the t, right? So this will become negative log of 0.5, which will be equal to the log of the 2, right? The value of the absorbance we will be getting it as 0.3010. This is gonna be the absorbance value for the solution A. Now for the second solution, that was, it says the optical density of this much concentration of the solution using the 1 cell. Okay, so now absorbance we know it is equal to the epsilon C into the L of it. For this particular solution, concentration is given to us and the length is given to us. Epsilon value is not given to us, that is molar absorptivity, right? So but from the solution A, if you see same compound I am having, so absorptivity it is gonna remain the same for both of them. I hope this is clear, because the same compound it is there, so absorptivity will be the same. So we can make use of the data of the to find the epsilon value from the solution A. Just the concentration of these solutions are different and different conditions have been given for A, B and C, but it is of the same compound. Okay, so from the first solution, the absorbance value we have got it as 0.3010. That will be equal to epsilon. Concentration was 0.1 mole per decimeter cube, and the length value it is 1 centimeter, right? But now this time the absorbance value, that is for the solution B, we have to find it out. This will be equal to epsilon. Now the concentration is 0.5 mole per decimeter cube, so that we can keep it, and the length value is 1 so 10 raised to the power of minus of 3 meters and into 10 raised to the power of 2 of centimeters, right? So with this centimeter will get cancelled out, these units are getting the cancelled from here, so epsilon and epsilon will get cancelled. Right, and this value, that will be 10 raised to the power of minus of 1, and this one will get cancelled out. So the absorbance, that is of solution B, it is equal to 0.3 into the 0.5 of it, which comes out to be as 0.15. This is the absorbance of the solution B, right? Now for the solution C, the transmittance of this solution is this much, that is 0.1. Now for the solution C, here I am writing it. Transmittance is given to us as 0.1. Absorbance for this solution will be negative log of this transmittance, which will be negative log of 0.1. That will be equal to the unity. That will be equal to the 1. right? So that means we are seeing that the absorbance is maximum for the solution C followed by the solution A. This is having the value of 1, and this was the value of 0.3010, and the least value we are having it of the solution B, which is 0.15. So the data was according to this. We are having C greater than A greater than B, so D becomes your correct answer. Okay, so this was the concept behind it. Now moving upon to our next question, that is from the year CSIR June 2015. So this one was remaining from 2011 to 2014. So that I have discussed now. Now moving upon to the next one, that is from 2015. So the question, it says the temperature dependence of a reaction is given by rate constant K is given to us as K is equal to AT square into the e raised exponential of minus of the E naught upon the RT. This is what is given. So two of the methods are there. One is the complete derivation part and other is directly making use of the Gardiner equation. Both of these I'll be telling you. So the first is through the derivation part. Let us look upon this. So take the natural log on both the sides. Take the So we have to take is natural logarithmic on both the sides. Take ln on both sides. So we will be getting is natural log of k equal to natural log of a plus of 2 times the natural log of t minus of the ea upon the rt. This is what we will be getting. Now differentiate this with respect to the temperature. So we will be getting d ln of the k upon the dt. This is equal to the d ln of the a with the dt. So this thing, it will be equal to the 0 only, because a is pre-exponential factor which is not including the any dependency on the temperature. So this can be equated to the 0 plus of 2 times the d by dt of ln of the t minus of d by dt of ea upon the rt. This is what we will be getting. So solving this, we will be getting d ln of k upon the dt. This is equal to 2 times the, now ln of the t differentiation with respect to the temperature, it will be 1 by t only. Now this will become plus of the ea upon the rt square. This is what we will be getting. Now the next we see, we know that d ln k by the dt. This is from the Van 't Hoff equation. This is equal to the ea upon the rt square. So use this relationship now and substitute into the equation that you have got it. So we will be getting ea upon the rt square, that is equal to 2 by the t plus of the e naught upon the rt square, right? So it becomes ea will be equal to 2RT plus of the E naught. So this will be the expression for the activation energy. So this is the complete derivation. So the answer is E naught plus of the 2RT. Option third will be the correct one. But this is directly from your Gardiner equation. Gardiner equation, according to which rate constant k is equal to a t to the power of m e raised to the power of minus of e naught upon the rt. After doing all this derivation that we have done it so far, so using that only, you will be getting overall activation energy ea is equal to e naught plus of the mrt, where m, this is the power of the temperature, power of the t that we are having in the given rate constant value. So here it was t square, it was present, so that is what m value you are getting it as 2. So you can see the same answer you are getting it. Either you can remember is this one for the from the Gardiner equation. If at some point you forget this thing, then this path you can follow it. Okay. So now moving upon to our next question we have is this one. So in this question it says for a reaction which is 2A plus B giving us 3Z, if the rate of consumption of the A is this much, which means minus of the dA upon the dt, this is 2 into 10 raised to the power of minus of 4 mole per liter per second, right? And the rate of formation of Z, we have to find it out. That means dz by the dt. This you have to find it out from the given equation, which is 2a plus of the b giving you the 3z. We can write the rate of the reaction. Theoretically the rate you can write it will be minus of 1 by 2 dA by the dt. This is equal to minus of the dB upon the dt of it. This is equal to 1 by 3 dz upon the dt of it. Now these two we need it. Minus of dA by dt is given and this we have to find it out. So both of these can be equated. So it will become minus of 1 by 2 minus of dA by the dt. This is equal to 1 by 3 into the dz upon the dt of it. So substitute the value which is known to us, that is minus of 2 minus of dA by dt, which is 2 into 10 raised to the power of minus of 4. This is equal to 1 by 3 into the dz upon the dt of it. So this will get cancelled out. Dz upon the dt value, it will be equal to 3 into 10 raised to the power of minus of 4, right? So in the rate of formation or the consumption values, we do not include the stoichiometric coefficients, but while writing the rate expressions, stoichiometry has to be included. That is the concept which was important in this. Okay, now moving upon to our next question. This question we are having, it says the equilibrium constant for a reaction which is methane plus 2 water giving you the CO2 plus the H2. So CH4 plus of the 2 water is in equilibrium with the CO2 plus of the 4 hydrogen, and the other is CO plus the water. This is in equilibrium with the CO2 plus the hydrogen. And the final equation you have to find is, that is CH4 plus the water is in equilibrium with the CO2 plus of the 3 hydrogen. So for rate constants for this one and this one are known to us. For the desired equation, if you see, we need is the methane that is present on this side. We need is this water, that is one water we needed. So here if I subtract this equation and this equation, I'll be getting CO2 and the hydrogen. So in the final answer it will be CO plus the what 3 hydrogen. Instead of the CO2 it will be CO. Okay, so make this correction. So what you can do is the rate constant K1, it will be product concentration, that is hydrogen raised to the power of 4 of it upon the CH4 into the water concentration raised to the power of 2 of it. And the K2 expression we will be getting it as, it will be CO2 into the hydrogen upon the CO into the water. This is what we will be getting. The final expansion, that is we needing it, K value, it is equal to the CO into the hydrogen raised to the power of 3 of it upon the methane into the water. So how can you, using this 1 and 2, how can you reach up to this 2 and this desired equation? That is, if you divide these two, K1 by the K2, if you do this, you will be getting, this is CO2 hydrogen to the power of 4 methane, and here is this water raised to the power of 2, and here is the denominator only, that is CO2 and the hydrogen concentration. This is for the K2, I am writing it CO upon the water. So if you solve this, you see it, the CO2 and CO2 is being cancelled out. Out of these two waters, this one water and one water will get cancelled out. This hydrogen 1 and 4 out of 4 1 will get cancelled out, so you will be seeing ultimately you will be reaching up to this answer only, which will be the Cu into the hydrogen raised to the power of 3 upon methane raised to the methane into the water, that will be raised to the power of 1 only. So that means this Kx expression, that is for the final equation, we have obtained it when we are taking the ratios of the rate constants K1 and the K2. So the correct answer will be the option C in this case. Okay, moving upon to our next one. This question, it says for an given ionic strength I, the rate of a reaction is given by log of K by K naught is this value. Which of the following reactions is? Follow the above equations. So this is from your primary salt effect. This is from our concept of primary salt effect, that is used to study the kinetics of the ions. Okay, so in that we get log of the K, this is equal to log of K naught, where K is the rate constant when these ions are in the solution, and K naught is the one when these are not present in the solution, plus of 2a times the Za into the Zb into the root of ionic strength. This is the expression. So you can see log of the K minus of the log of K naught, this is equal to 2a times the Za into the Zb into the root of ionic strength, right? Log of m minus of log of n, we can write it as log of m by n, which will be equal to 2a times the Za into the Zb into the root of I of it. This value it is given to us as minus of the 0.4 into the sorry 0.4 into the 0.5, 4 into the 0.5, 1 into the I raised to the power of half of it. This will be equal to 2a times the Za into the Zb into the root of I of it, right? So this I raised to the power of half is being cancelled out. This a value, which is the Debye-Huckel's constant, its value is also the 0.51. So this 0.51 and this will get cancelled out. So with this 2, this 4, we will be getting it as minus of 2, which implies that the product of these charges, which is Za into the Zb, this is equal to the minus of 2. That means from the given options we have to choose the one in which the product of the charges of these ions, it is equal to minus of the 2, that is gonna give us this rate expression. Okay, so in the option A, it is S2O8 2 minus and I minus. So the charges are minus 2 and minus of 1, which is gonna give the product as plus of the 2. So we need is the minus of 2. So this can't be our answer. Next is CuNH3 5Br2 positive. So plus 2 charge and OH negative. So plus 2 and minus of 1, plus 2 and the minus of 1, it is gonna give us the minus of 2. So that means this will be the correct answer in which we will be getting the product as minus of 2. Okay, so I hope this is clear. Now moving upon to our next question, that is this one. It says the intensity of the light beam, it decreases by 50% when it passes through a sample of 1 centimeter path length. The percentage of transmission of the light passing through the same sample but of 3 centimeter path length. So what it means to say is, suppose this is the cuvette that we are having. This is the cubical type of the block that is called as the cuvette. In this, what we do is we fill our sample. This is the sample we have filled it. The length of this tube, that is path length, it is 1 centimeter. In this, when you are passing the light, which is of the intensity I naught, after passing through the sample, the intensity of the light which is coming out of it, it will be the I. It is saying that the intensity, it is decreases by 50%, which means the final intensity that you are getting upon the original one, it has decreased now by 50% decrease we are having. That means the transmission that is taking place, it is 50% of the original one. Suppose 100% we have transferred from this sample, the outside that we are getting is only the 50% of it. Okay, so now instead of the 1 centimeter, this same sample it was taken and it is placed in the cuvette which is of the 3 centimeters. So now here this tube that you are having, 3 of the such blocks are present. Each of them it is of the 1 centimeter. So my block lengths are different, but imagine that these are of the 1 centimeter only. Okay, so this is also the 1 centimeter. So again this light we have passed is, here the sample is present. Now this light we have passed is, which is of intensity I naught, and the intensity of the light which is coming outside, now what is that gonna be? That is what they are asking to us. So what I did was I passed a light of the 100 centimeter intensity. When it is passing through the 1 centimeter cuvette length, it is passing, 50% decrease I am observing in this. That means in the next path when it is traveling, 50% of the light intensity has already decreased. Right? Now when it is passing through the next 1 centimeter path length, again 50% decrease it will be there. That will be, originally now it intended was 50%, so half of this it will be 25% that is gonna enter into the third cell. Now in the third cell again a 50% decrease it is gonna be there in the from the after passing through the sample. So the final intensity of the light that you will be observing, it's gonna be still half of 25%, that is 12.5%. I hope it is clear. So the value of the light that after passing through 3 centimeter path length, it's gonna be 12.5%. This is one of the way. One more thing you can see is that transmittance, we know it is multiplicative in the nature. So when it is passing through the first cell, so it's gonna have the transmittance T1. When it's passing through the other one, again the same transmittance, and the third one, that is T1. In all of the cases 50% transmittance we are observing. So 50 into 50 into the 50%. Now percentage of transmittance you have to find it out. So multiply this whole with the 100. You will be getting your percentage. So that will be 50 upon 100 into the 50 upon 100 into the 50 upon 100 into the 100, which we will be getting it as 100 upon the 8. That becomes the 12.5% again. Okay, so either this way, either that way, both of them you can use it. Transmittance is multiplicative in the nature. This is the concept you are using it. Okay, so this was the answer, that is the option D. Now moving upon to the next one. This question, it says consider the following parameters with reference to the fluorescence of a solution. What is fluorescence? Firstly, so in the Jablonski diagram, we observe this thing, that you have different states present in it. First is, this is known as the singlet ground state. This is singlet first excited state, and this is your triplet first excited state. Right? So in this, if suppose a particle it is present, we provided energy of the h nu supposed to it. The particle is gonna go to the excited state by making some of the absorbance. So this is the absorbance is taking place. Now excited state is unstable, so particle if it is coming back to the ground state with the emission of some light, that is of the h nu energy, that is it is coming out. So this process it is called as the fluorescence. The particle is coming back with the emission of some light which is of the h nu and h nu energy. This process is fluorescence. Right? So now we have to look upon the correct answer for the enhancement of the fluorescence. We have to look upon to the factor with which this fluorescence process it is gonna increase. Right? So the first it says the molar absorptivity of the fluorescent molecule. So this is true. The molecule which is getting being, suppose this is one of the molecule and the other molecule you are having, their molar absorptivity are different. So fluorescence will be dependent upon their molar absorptivity, that is their epsilon values, right? So this statement is the true. Next one, it says the intensity of the light source which is used for the excitation. Again, this h nu energy that we are providing, its intensity is gonna affect the amount of the fluorescence that we are observing. More is the intensity, then particle will be coming back with the more energy, so more fluorescence tendency it is there. So again, there will be enhancement in the fluorescence process, right? Next is with the dissolved oxygen. So you might have encountered a topic that is called as quenching. So with the quenching, what basically happens, the particle that you have excited, its energy it transfers to the other molecules. Here the other molecule is the oxygen molecule. So that means when it is returning back to the ground state, so the intensity of the light that it is releasing or the fluorescence process that it is carrying out, it will be decreased because it is acting as like inhibitors now, and quenching of the fluorescence process it is taking place. So this is not gonna enhance my fluorescence process, rather it is gonna decrease the fluorescence process, right? So this is not involved in it. So the correct answer for the enhancement is first and the second only. So the option A, it becomes the correct answer. Okay, moving upon to our next question, that is this one. It says according to the transition state theory, the temperature dependence of a pre-exponential factor of a reaction between a linear and a non-linear molecule. So we are having a linear with the non-linear molecule, and this is forms a product going through the non-linear transition state. So this is non-linear activated complex, or the transition state has been formed, and then this is going to the product P. So according to our transition state theory, there exists an equilibrium between the reactant species and the transition state. So this is what this theory it states to us. So for this one, the rate constant that we write, it is equal to 8 kBt. Sorry, this is for the collision one. So this is for the transition state, we write the rate as kBt by the h, right? kBt by the h into the k dash. This is the rate constant expression that you get for it. So now this k dash value that is present, this is the equilibrium constant, which is the no, a partition function of the transition state you are writing it, and in the denominator here it will be the partition function of the linear molecule into the partition function of the non-linear molecule. So this is basically your equilibrium constant, that is k dash. So product concentration upon these reactant species, their partition functions are involved in this. Okay, so for the non-linear molecule, now I am having non-linear transition state. This is gonna have the translational partition function, and number of the translational degrees of freedom is 3, so it will be raised to the power of 3, and the number of the rotational degrees of freedom in this, it is also gonna be 3, so their partition function will be also raised to the power of 3. For the linear molecule, it includes the translational partition function raised to the power of 3, and the rotational partition function, its power will be raised to the 2. Right? For the non-linear molecule, again it includes the partition function, that is translational partition function raised to the power of 3, and the rotational partition function raised to the power of 3. Right? Now these partition functions that we are writing, they are dependent upon the temperature raised to the power of half of it. So it will become T raised to the power of 3 by 2, because each of them is raised to the power of half, raised to the power of half, so 3 are there, so T raised to the power of 3 by 2. Similarly here also T raised to the power of 3 by 2 upon the T raised to the power of 3 by 2 into T raised to the power of 2 by 2 into T raised to the power of 3 by 2, T raised to the power of 3 by 2. So from here if you see, So this 3 raised to the power of 2. This one and this is getting being cancelled out. This and this is getting being cancelled out. So we are getting it as k dash equal to 1 upon t into t raised to the power of 3 by 2. That is equal to 1 upon t raised to the power of 5 by 2. We are getting it. So now the rate constant k that we have written, this is the pre-exponential factor, that is a. A will be equal to the kbt by the h up into the 1 upon t raised to the power of 5 by 2, right? So this is we are getting as t raised to the power of minus of 3 by 2 into the kb by the h. So we are seeing that the pre-exponential factor a, it is proportional to t raised to the power of minus of 3 by 2, or it is t raised to the power of minus of 1.5 of it. So that means the pre-exponential factor is proportional to the option D, which says t raised to the power of minus of 1.5. Right? Now moving upon to the next question we have is this one. In a photochemical reaction, the radicals formed according to this equation, if I is the intensity of the light they have observed is the rate of the overall reaction, it is proportional to. So rate, it will be written into the final step which is given to us. So rate, we can write it as rate constant K2 into the C2H5 square, it is there. Now C2H5, it is the intermediate because it is formed in the first step and getting being consumed into the second step. So SSA we have to apply on the C2H5. So look in the equations where this C2H5 terms are involved. So we have is C4H10 plus the H nu. This is in equilibrium with the 2C2H5. This is the rate constant K1. This is K inverse. So here this equation I can break it like this. C4H10 plus the H nu with the rate constant K1. It is giving us 2C2H5. So 1 by 2 d by dt of C2H5, this is equal to, so now here the with this is the rate constant and the intensity of the light which is getting being observed is I intensity of the light, with that it is observing. So rate for this first step in which there is C2H5, this formation it is taking place, it's gonna be equal to the intensity of the light only. Now in the second equation that we are getting it is C2H5 giving us C4H10. This is with the rate constant K inverse. So minus of 1 by 2 d by dt of C2H5. This is equal to K inverse of the C2H5 whole square. This is what we will be getting. And the third equation, which includes the 2C2H5 with the rate constant K2, it is giving us C2H6 plus the C2H4. So for this 1 by 2 minus of the 1 by 2 d by dt of C2H5, this is equal to the K2 times the C2H5 square. This is what we will be getting. So now all these values of the d by dt of C2H5 that we have obtained it, combine all of this so that we can apply the SSA over it. So we can say d by dt of C2H5, this is equal to 2 times the I. Next is minus of the K inverse of the C2H5 square and the minus of the K2 times the C2H5 square. This we can write it, this is equal to the 0. So we can say 2I upon the K inverse plus of the K2. This will be equal to the C2H5 squares square, it will be equal to, now the rate expression that we got, it was equal to K2 times the C2H5 whole square, K2 times the C2H5 whole square. Now its value you can substitute it, K2 times the 2i upon the K inverse plus of the K2 into the, so 2i upon the, this is the value you are getting. So we can see here that rate, it is proportional to the intensity, that is I over here. So this is what is asked, that the rate of the overall reaction, it is proportional to, so that is I. So here no C4H10 term is involved, so it is proportional to the I only. So the correct answer becomes the option A in this case. Okay. Next one is this question. For the following reaction, dB by the dt, it is given by. So the reaction we are having is A is in equilibrium with the 2B, rate constant K1 and the K inverse. So in this we can break it A to the 2B with the rate constant K1. So 1 by 2 dB by the dt. This will be equal to the K1 times the A, right? Next is 2B giving us the A. This is with the rate constant K inverse. So it will be minus of 1 by 2 dB by the dt, because there dB 2B was getting being formed. So here the positive rate expression we have written. Here dB is the reactant, 2B is the reactant. So it will be minus of 1 by 2. This is equal to K inverse of the B square, right? And the other equation, that is B giving you the C with the rate constant K2. So minus of dB by the dt, this is equal to the K2 times the concentration B over here. So we are asked to find the value of dB by the dt. So combining all of these three, we will be getting 2 times the K1A minus of the 2K inverse of B square minus of the K2 times the B. It's gonna be equal to dB by the dt. So this is gonna be the expression. So here it's not the half, it's the square you are having. So here is this power, that is 2, we will be having it, right? So that means 2K1A minus of the 2K inverse of the B square minus of the K2 times the B. Option D, it becomes the correct answer in this. Okay. Now moving upon to the next one. So these were all the questions that were from the June exam conducted in the year 2015. Now beginning with the 2015 December exam, question it says is, according to the transition state theory, one of the vibrations in the activated complex is a loose vibration. This we know it. The partition function of this loose vibration is equal to, so for this loose vibration, what is the partition function, that we have to tell them. So we know that Q vibrational, it is equal to 1 upon 1 minus e raised to the power of minus of h nu upon the kBt of it, right? So now it is a loose vibration, which means nu value, which is the stretching frequency. This is very small, we are having it. It is very small, which implies this product of h nu that I am having, this is very small as compared to the kBt. From the given conditions, this thing we are having. Now h nu by the kBt, if I see, this is suppose equal to the x. So now h nu is very small as compared to the kBt, which means this x value, it is less than the 1, right? Now this Q vibrational that we have written in terms of the x, if I am writing it, it will become 1 upon 1 minus e raised to the power of minus of x. This expansion, that is of e raised to the power of minus of x, we can write it as 1 minus x plus of the higher terms, it will be there. So generally these higher terms we ignore it. Okay. So Q vibrational, it will be 1 upon 1 minus e raised to the power of minus of x, it will be 1 minus of x plus higher terms that we are ignoring it. So being the small, they can be ignored. So this 1 and 1 will get cancelled out. So Q vibrational, it becomes equal to the 1 upon the x only, right? So this x value we can now substitute it. So Q vibrational, it was 1 upon the x, that will be equal to h nu upon the kBt, so that is going in the numerator. So this is the partition function of that loose vibration, which is equal to the kBt upon the h nu. So this is the answer for it. Okay. Now moving upon to the next question we have is this one. It says Vmax and the Km for an enzyme catalyzed reaction. Vmax means the Rmax value is given to us and the Km value is this much respectively. The rate of reaction when the substrate concentration is this one. So we are having an enzyme catalyzed reaction which includes the enzyme plus the substrate. They are in equilibrium with the ES. The rate constants are K1 and the K inverse. In the second step, this ES, it gives us the product P with the rate constant K2 for this reaction. This is the one. Now for this, the rate value that we find it out, this is equal to R max into the S upon the Km plus of the S. Right? So now these values are given, that is of the V max, which means the R max value. Substitute this, which is 2 into 10 raised to the power of minus of 3. Substrate concentration is 1 into 10 raised to the power of minus of 6 upon Km value, which is 1 into 10 raised to the power of minus of 6 plus of the S, which is 1 into 10 raised to the power of minus of 6. This comes out to be as 2 into 10 raised to the power of minus of 3 into 10 raised to the power of minus of 6 upon 2 into 10 raised to the power of minus of 6. So this 2 and 2 will get cancelled out. These will get cancelled out. This comes out to be as 10 raised to the power of minus of 3. So that means the R value that we are obtaining, it is 1 into 10 raised to the power of minus of 3 second inverse. So this is the answer that is in the option B, it is given to us. Right? Now moving upon to our next one, we are having is this. It says the first order rate constant of a unimolecular gaseous phase reaction A to the product B that follows the Lindemann mechanism is 2 per second at pressure PA is equal to 1 atmosphere, and second one is given to us, rate value is 4 second inverse when the pressure is 2 atm, the rate constant of the activation step. So in the unimolecular reaction, what basically happens is we have two of these A and A. They undergo there is an equilibrium with the rate constant K1 and this is K inverse. Here the excitation takes place that gives the one of the activated species and the other is as it is, and the other this activated species in the next step with the rate constant K2, it gets converted into the product P. This is the Lindemann mechanism for the unimolecular reaction. Now in this the K1 that I am having, this is called as the rate constant of the activation step. Rate constant of the activation step. So whenever two of the observed rate constant, so overall reaction, this mechanism we are saying it is taking place, but in actual A is being converted into the product P only. So this possesses the rate which is called as the rate constant as the observed rate constant. Right? If we have two of the observed rate constant values, in that case you can use this thing, which is observed rate constant A minus of the 1 upon the K dash, which is the second observed rate constant. This is equal to 1 upon the K1, which is the rate constant of the activation step, into the 1 upon PA, which is the pressure for the A conditions, minus of the PB. So now these values are known to us. Substitute these and find the answer. 1 by the K dash, that means the observed rate constant at the pressure 1 atm that you are having. This will be equal to 1 by 2 minus of the 1 by 4. This is equal to the 1 by K1 into the 1 by pressure, which is 1 atm minus the 1 by 2 of it. Right? So just solve this now. So we are having is 1 by 2 minus 1 by 4, which comes out to be as 2 minus 1 upon the 4. This is equal to 1 by K1, 1 upon the 1 minus the 1 upon the 2. So it again becomes 2 minus of 1 upon the 2 only. So it becomes 1 upon the 4 is equal to 1 upon the K1, 1 upon the 2. So that is 2. So K1 value, it comes out to be as 2. 2 ATM, 2 ATM inverse, second inverse. ATM inverse, second inverse. So this is gonna be the answer that is given to us in the option B in this case, right? Next is this question. So this is from your graphical methods that are used to find the order of a reaction. So this is graphical method to find order of the reaction. So the plot is given for the rate versus the this concentration versus the time plots are given to us. So we have to find these curves are belonging to which of the orders. So firstly, for the zero order reaction, if we see, the integrated rate expression is A naught minus of A, it is equal to KT, which means A value is equal to A naught minus of the KT of it. That means Y is equal to the mx plus of the C. So the slope value in this case, we are having it as minus of the K. So in this, the first plot, if you see, that is for concentration versus the time plot that is given to us. Here a negative slope we are having, which represents it is minus of the K, and some of the intercept value is also there, which means the first plot, it corresponds to the zero order. Now the second one, that is for the second order, if you see, for the second order, why not the first order? Because in first order, integrated rate expression includes the natural logarithmic terms. So we are taking the second order now. It will be 1 by A minus the 1 by A naught. This is equal to the KT. So 1 by A is equal to the 1 by A naught plus of the KT of it. So Y is equal to the mx plus of the C. So the plot for the 1 by the concentration versus the time, it gives us the positive slope. It gives us the positive K value. So that is what is shown in the curve. 1 by R versus the time, a positive K value as the slope we are having. So this data, it corresponds to the second order curve, right? So 0 and the second one, answer becomes the option C. Next is this question. The rate of a reaction R1 and R2 at the concentration C1 and C2 of the reactants respectively, the order N of the reaction is with respect to the reactant is given by. So R1 rate will be equal to the K rate constant into the concentration C1 raised to the power of N of it. R2 rate expression, it will be rate constant K into the C2 raised to the power of N of it. Take the ratios of this R1 upon the R2. This is equal to the C1 upon the C2 raised to the power of N of it, right? So take the log on both the sides now. Log of R1 by the R2. This will be equal to N times the log of C1 upon the C2 of it, right? Log of M by N, we can write it as a log of the M minus the log of the N. This is equal to N times the log of C1 minus the log of C2 of it, right? So the N value will be equal to log of the R1 minus the log of R2 upon the log of the R2 upon the log of C1 minus the log of C2 of it. This is gonna be the N value that is given to us in the option A, right? Now next is we have this one. So from the year 2015, all the questions we are done with that. Now this is from the June 2016 exam. The experimentally determined rate law for a chemical reaction is rate expression is this much, this one, and rate is dependent upon the slowest step or the RDS step of the reaction. So the rate determining step, rate has been written in terms of that only as per your rate law. So it is involving NO2 raised to the power of the 1 only. So that is given to us in the option C in this case, right? In others, if you see, in the first one, it was raised to some of the stoichiometry it is given. In the B, some other B and D, some other terms are included with it. So C is the answer for this one. Next is this: for a chemical reaction where the aqueous species are present, choose the correct statement. So this is from your primary salt effect, statement based question it is there, from the primary salt effect. According to this, the expression that we get it is log of the K, it is equal to log of K naught plus of 2a times ZA into the ZB into the root of ionic strength. If I see a plot for the log of K by the K naught, this will be equal to 2a times the ZA into the ZB into the root of ionic strength. So the plot, if you see, it is y is equal to the mx, right? So that means the slope value that I am having, it is dependent upon the ZA and the ZB values, right? So here if ZA, ZB, they are both product, it is positive, which means my slope it is gonna be positive. So the plot, if you see, it's gonna look like this for the log of the K upon the K naught versus the root of ionic strength, right? If both these are the same charges, if ZA and ZB are the same charges, are same, in that case you see log of K by K naught with the ionic strength, a positive slope, the plot will be represented like this, which means when both the signs they are the positive, slope is positive. If opposite charges I am having, if opposite charges are present, that means either ZA is positive, ZB is negative, or you can say it is negative, ZA is negative and ZB is positive. In this cases the product we will be getting it as the negative, which means the slope value it is gonna be negative, that is represented like this with the negative slope. That means if both the charges are the same, with the increase in the ionic strength, the rate of the reaction it is gonna increase. Whereas in the opposite case, if I see, with the increase in the ionic strength, the rate of the reaction it is gonna decrease in this case, right? Next thing, if you see, if you change the dielectric constant of the solution, if you change the dielectric constant, with the increase in the dielectric constant value, which is the epsilon, the rate of the reaction it is gonna increase when same charges are present. Whereas if the dielectric constant value it increases when the opposite charges are present, rate of the reaction it is gonna decrease in that case. Okay. Next is the about the entropy. When same charges are present, then the entropy of the activation that you have, entropy of the activation, it is gonna be negative. If both the charges are present, it is gonna be negative. Whereas if both the charges are opposite, in that case, the entropy of the activation it is gonna be positive in that case. So these things you just remember from the primary salt effect if same charges are present or the opposite charges. So based upon this concept, if I see the first statement, it says increase in the pressure increases the rate constant. So is it so that you are seeing in the rate expression any pressure term is involved? The answer is no. It is dependent upon the charges of the product of these charges which is present and the ionic strength values. Right? So this is pressure term is not involved. So this is the incorrect one. Next test says increase in the dielectric constant increases the rate constant value. So it is your true one, because here you see both the charges which are present upon the ionic species are the same only, here minus and here also the minus, same charges are present. So with the increase in dielectric constant, this value, rate constant value, it increases. Next test says is increase in ionic strength decreases the rate constant. So it is incorrect. We have seen this when same charges are present, with the increase in the ionic strength values, the rate constant values it increases and not decreases, right? Next is entropy of activation is positive. So same charges, entropy of activation it is negative, not the positive. So the correct answer is the option B in this case. Okay. Next one is this question, you have it. If the experimentally observed rate constant is greater than the maximum value of the rate constant obtained using the hard sphere model of the collision theory, relationship between the impact parameter and the sum of the radii is. So this impact parameter that you observe in the collision theory, it is denoted impact parameter. It is denoted with the B value, and this is the experimentally determined rate constant only. This is the experimentally determined. Okay, so here if you see, if the impact parameter value it is equal to the 0, in that case the head-on collision it takes place between the hard spheres. Head-on collision it takes place if this B value, which is experimentally determined rate constant value, this is less than the sum of the radii, which is R1 and the R2 of the hard spheres. In this case collision is possible. Now from the given data it is saying experimentally observed rate constant, which means the B value they are talking about, it is greater than, so it is more than the maximum value of the rate constant, which is equal to the R1 plus the R2. So this condition it is given, that is, in this case the possibility of collision it might be negligible or may not be there. But this is the one when B is equal to 0 or B is less than the sum of these radii, in that case collisions are possible. So from the given conditions the answer it becomes the option C. Okay. Next is this one. Half-life for a third order reaction. C0 is the concentration. For the nth order of the reaction, we know that T half value it is equal to 2 raised to the power of n minus 1 minus of 1 upon the rate constant K into A naught raised to the power of n minus of 1 into the n minus of 1 of it. That is gonna be equal to 2 raised, now n value here it is 3, so substitute that, 2 minus of 1 minus of 1 upon the K into the A naught raised to the power of 3 minus of 1, it was 3 minus of 1, A naught raised to the power of 3 minus of 1 into 3 minus of 1. This is equal to, so 2 to the power of 2 minus of 1 upon the 2k A naught square. Instead of the A naught, C naught is used. So that becomes 3 by the 2 k C naught square. Right, so this is gonna be the T half for the zero order reaction with the initial concentration C naught. So the answer it becomes the option A in this case. Right. Next one is, this is from your December exam that was conducted in the year 2016. So the statement it says that for a reaction with the activation energy of this much, the ratios of the rate constant at 600 kelvins and 300 kelvin is, so two of the rate constants are given, natural log of the K that will be at 600 upon the natural log of K upon at the 600 upon the K or the 300. This is equal to EA upon the R into the 1 by the T1 minus the 1 upon the T2 of it. Right. So now this K ratios we have to find it out. Activation energy it is given to us as 49.8. Now this is kilo. So 10 raised to the power of 3. This will be in the joules per mole upon the R value, which is 8.314 joule per mole per Kelvin into the 1 by temperature, which is 300 minus of the 1 by T2, which is 600 kelvins. So this is equal to the natural log of the K, 600 upon the K, that is 300. Right. So just solve this values. It will be 49.8 into 10 raised to the power of 3. This joule per mole term is being cancelled out. This is in Kelvin, so this Kelvin and per Kelvin is being cancelled out. Here it is 8.314 into 300 into 600. Here in the numerator the difference will be of 300. This e raised to the power, you will be having it, or you can say it, this thing we are getting, this is equal to natural log of k at 600 upon the 300. Solving this, the value you get it as approximately 10 only. So the rate constants ratio at 600 to that of 300, it will be equal to e raised to the power of 10 of it. So this is gonna be the answer that is given to us in the option D. Okay. Next is this one. According to the transition state theory, the plot with the slope equal to minus of delta H by Rs. So according to the transition state theory, we say there is an equilibrium. Suppose these are the reactant species involved. So this is the K dash, which is the equilibrium constant for this. There is the intermediate is getting being formed in between, and then it results into the product P formation. This is rate constant K2, we can say it. So according to the TST, this equilibrium is present between the reactant terms and the transition state, right? So for this, the rate expression that we write, it is equal to kBt by the H into this X dash concentration, right? Now to find this X dash concentration, the equilibrium constant, you can write it as this. It is equal to the product concentration upon the reactants which are involved in it. Okay, substitute this, or the X dash value you can find it out from here, which is K dash into the A into the B. Now this X dash value you can substitute into the rate expression. We get the rate as kBt by the H into the K dash into the A into the B's, right? This is the equation. So the reaction that is taking place is A plus B, it is giving you the product P only. So the rate constant for this, it is gonna be K only. So rate expression in this case, we can write it as K into the A into the P, right? So comparing these two now, because both of them, they are the rate expressions only. So we get the rate constant value as, it is kBt upon the H into the K dash. This is the rate constant value that we obtained, right? So now here this K dash value that you are having, this you can solve it in two of the methods. One is called as the thermodynamic approach, thermodynamic approach, and other we are having is, this is statistical approach, statistical approach. Okay, so here now delta H is involved, which means the thermodynamic process we are gonna use it. Now in thermodynamics, we have learned that delta G dash, this is for the activated complex, it is equal to minus of the RT natural log of the K dash, natural log of K dash. This is the equilibrium constant that we will be having. From here, delta G dash upon the RT minus of this, it will be equal to the natural log of the K dash, right? So we can see that K dash value, it is equal to e raised to the power of minus of delta G dash upon the RT of it, right? Now we know one thing more, that delta G dash, it is equal to delta H dash minus of the T delta S dash, right? So substitute this to find your K dash. It will be e raised to the power of minus of delta H dash minus of the T delta S dash upon the RT of it. This will be equal to e raised to the power of minus of delta H dash upon the RT into the e raised to the power of delta S dash upon the R of it, right? So this thing now you can substitute in your expression, that was this rate constant value that you got, K value, it was equal to kBt upon the H into this X dash value, this K dash value that you have got it, it is e raised to the power of minus of delta H dash upon the RT into e raised to the power of delta S dash upon the R of it, right? So you can take this temperature on the other side. It becomes K by T equal to the Kb upon the H e raised to the power of delta S dash upon the R into e raised to the power of minus of the delta H dash upon the RT of it, right? Take the natural log on both the sides. Ln of the K by the T, this is equal to ln of Kb upon the H into e raised to the power of delta S dash upon the R minus of the delta H dash upon the RT, right? If I see a plot that is for natural log of K by T versus 1 by T, natural log of K by T versus 1 by T, in this case it will become Y is equal to the mx plus of this, that will be this term, it is gonna be the intercept in that case, this value, right? So that means slope value which we are getting it as, it is minus of the delta H dash upon the R, and this is what we had to calculate. That is, by making a plot for the natural log of K by T versus 1 by T, I'll be able to find the value of minus of delta H dash upon the R of it. So the answer becomes the option C in this case, right? Now moving upon to our next question, that is this one. A reaction goes through the following elementary steps. Assuming the steady state approximation can be applied to C, on doubling the concentration of A, the rate of production of D it will increase by. So it is asking rate of production of D, which means D by dt of the capital D, it is being asked to us. So it is given in the mechanism that this is the slowest step of the reaction. So this is the RDS step of the reaction, which will be equal to rate, we can write it as K2 into the A's concentration into the C's concentration. Now C, it is an intermediate formed in the reaction and consumed during the course of reaction, right? So now the C's concentration we have to find it out. So if you observe the first equilibrium that is given to us, it is written that it is your fast equilibrium. That means in this case the equilibrium approximation can be used. Equilibrium approximation can be applied. Had it been written that fast, it is not the fast one, in that case SSA you have to apply in that case. So here it is written that steady state you have to apply on the C, but equilibrium approximation too you can use it. Okay, so I'm making use of the equilibrium approximation, that is A plus B is in equilibrium with the 2C, rate constant K1, and this is K inverse. So rate constant K1 upon the K inverse, that is ratio of the rate constant of the forward to the backward direction. This will be equal to the C's concentration raised to the power of its stoichiometry upon the A into the B's concentration. So from here C's concentration, it is gonna be C square concentration, it is equal to K1 upon the K inverse into the A into the B's concentration. So substitute this value in the rate expression, which is of the formation of the D. This will be equal to K2 times the A's concentration into the C's concentration. Now C square value we have got it as K1 upon the K inverse into the A into the B. So C's value, it is gonna be equal to the half of it. K1 upon the K inverse, its power raised to the power of half, A to the power of half, and B to the power of half only. So this C value we can substitute. So it is K1 upon the K inverse raised to the power of half. It is A to the power of half, B to the power of half of it. So it becomes K2, K1 by the K inverse raised to the power of half into the A raised to the power of 3 by 2, B raised to the power of half, right? So you can see the rate of formation of D, it is proportional to A's concentration raised to the power of 3 by 2. So D by D of the dt, this is proportional to A's concentration raised to the power of 3 by 2 of it. So if you are doubling the concentration, this is given, on doubling the concentration of A, how is the rate of formation of D gonna be affected? So instead of A, now the concentration is 2A. So in that case, d by d of the dt, so this will be equal to 2A raised to the power of 3 by 2. So this is proportional to that. So it is 2 raised to the power of 3 by 2 into A raised to the power of 3 by 2, which means the rate it is becoming 2 root 2 times the previous rate, which was A raised to the power of 3 by 2. So it becomes this much, right? So d of d by the dt, it will become 2 root 2 times. So that means the correct answer in this case is the option D, right? Next is this one. So for two of the reactions have been given to us. First reaction, X plus Y is combining to give the Z, and in the second, M plus N is combining to form the P product. According to the collision theory, the ratios of their squares of their pre-exponential factors of the reaction 2, which is A2, and 1 for the reaction 1, it is A1. At the same temperature, A2 by the A1 square, it is equal to. So we know that for the collision theory, the pre-exponential factor that you have, it is root of 8 kBt by the pi mu into the pi sigma square into the Na into the rho. This is the pre-exponential factor that we have, right? Because rate constant k, we write it as root of the 8 kBt by the pi mu into the pi sigma square into the Na into the rho into e raised to the power of minus of e naught upon the RT of it. So rate constant k is a into e raised to the power of minus of e naught by RT. So from that, the pre-exponential factor you are getting is this one. So here if I see the pre-exponential factor that is present, it is proportional to the the sigma square values, and it is inversely proportional to the root of the mu values. Other things, if you see it, kb, pi, mu, Na and the rho, for the reactions they are the same. Temperature is also the same because both of them, the reactions, we have carried it out at the same temperatures, right? Now this sigma value we have to find it out. So sigma for the first reaction, it will be xy. This will be equal to the sigma x plus the sigma y upon the 2, because this is pi sigma square, it is the area that we write it. Now the diameter values have been given to us in the table, so we need is the radius value, but for that we divided with the factor of 2. So sigma for the x, it is given us as 0.3. For the y, it is given us as 0.5 upon the 2, which we will be getting it as 0.4 value, right? Similarly, sigma for the mn, it will be equal to the sigma of the m plus of the sigma of the n upon the 2, that is equal to 0.4 plus 0.4 that upon the 2, that is equal to the 0.4, which means for both of them the sigma value that we are getting, it is the same. We need is the ratio now, that is A2 by the A1. So A2 upon the A1, sigma for that is it is constant. This was sigma 2 square upon the root of the mu 2 into the sigma of the 1 square upon the root of the mu 1, right? The sigma values we have got the same, so these you can cancel it out. So this becomes equal to the root of mu 1 upon the mu 2. So the first reaction, it was between the x and the y. So there will be this mu is the reduced mass for them, so it will be mass of x into the mass of y upon the mx plus the my. This is in the under root. This is for the mu 1 we are having it. Now for the mu 2, that is for the reaction between m and n, so it will be mass of m plus the mass of the n, sorry, into the mass of the n, m1 into the m2 into the mass of n upon the mass of the m plus the mass of the n. Now these values are given to us, that you just have to substitute it. Mass of the X, it is given us as 5, and of Y it is given us as 20. So this will be equal to 5 into the 20 upon the 5 plus of the 20. This is in the root, and in the denominator we are having the value as 10 and 10. So it will be 10 into the 10 upon the 10 plus of the 10. So this becomes equal to root of the 100 upon the 25 into the 20 upon the 100. This value it will become 100 and 100 will get cancelled out. That is equal to root of 20 upon the 25, which is equal to 4 by 5 in the under root. Right? This is the value of the A2 by the A1. A2 upon the A1, which is equal to root of 4 by 5. Now the square of it, A2 by the A1 square, this will be equal to root of 4 by 5 square, that is equal to 4 by 5. So the correct answer, it becomes the option A in this case, right? Moving upon to the next one we are having is this question. It says the rate of an acid catalyzed reaction in the aqueous solution, it follows the rate equation as K X positive Y2 negative H positive, which means 3 of the ionic species are involved in the reaction. Now if K16 and K4 are the rate constants for the reactions at the ionic strength 16 and 4 moles per liter respectively, natural log of K by the 16 in terms of the Debye-Huckel constant B is that we have to find it out. So now when the 3 ionic species are involved, so again this is from your primary salt effect. If 3 ionic species are involved, we write the expression like log of K, it is equal to the log of the K naught plus of the 2 times the ZA into the ZB plus of the ZB into the ZC plus of the ZC into the ZA into the root of the ionic strength. So now the ionic strengths are given to us as 16 and 4. We need is the ratio of the log of the K4, log of the K4 upon the log of the K. When the ionic strength is 4 moles per liter, we can write the expression like log of the K4. This is equal to the log of K naught plus of the 2A times, instead of the A, the Debye-Huckel constant they have used is B. So that we can write it like this. Here I missed it, that you to add it. Okay, so ZA, that is charge on the ionic species 1, which is given us as plus 1. Next is the charge on the second ionic species, which is Y minus 2. So that minus 2 it will come, plus of ZB, which is minus of 2, ZC, which is charge on the third ionic species, which is my plus 1, plus of the ZC, which is plus 1, and the ZA, which is again the plus 1 into the root of the ionic strength, which is the 4 in this case, right? So log of the K 4, it will become equal to the log of the K naught plus the 2B times, it will be minus of 2 plus of the 1 into the root of 4, that you can write it as 2 only. It will be 2 only, right? So minus of 4 plus of 1, it becomes the minus of 3 into the 2 into the 2B. This is plus log of the K naught. This is equal to the log of K4. This will be equal to log of the K naught minus of the 12B, right? This is the value for the log of the K4. Now for the 16, when the ionic strength it is given, so in that case log of the K16, this is equal to the log of the K naught plus of the 2B ZA into the ZB. That sum we have calculated, it was minus of 3 into the root of ionic strength, which is root of 16. So this becomes equal to the log of K naught plus of the 2B into the minus of 3 into the 4. So 4 3s are 12, 2s are 24. So it becomes the minus of 24B in this case. This is equal to log of K naught. This is equal to the log of K when the ionic strength is 16 moles per liter. So these two equations we have got it. So we can subtract these two because we need to take the ratios of this. So this is K4, this one. Okay. So log of the K4 minus of the log of the K16, it will be equal to log of the K0 plus of the. In the previous case, it was log of the K4 we have calculated as minus of the 12b minus of log of the K0 minus of the 24b, right? So this log K0 and log K0 value will get cancelled out. We are left is with minus of 12b plus of 24b, that we get it as 12b. So this log of m minus of log of n can be written as log of the m by n, which is log of K4 upon the K16. So the value we are getting it as 12b. So this is the answer. So in the options, if I see, that is given to us in the option D. Okay, so this was the last question that was to be discussed in this video. So with this, we are done with our paper that was conducted in the year. Which year it was? It was 2016 December exam. So we have discussed 2015 and 2016 paper in this video, right? So now the remaining parts of it, that is the next questions of the next papers that we will be having, that we will be seeing in the upcoming class. So I hope all the questions are clear to you. If you still have doubted any of the questions that I have discussed so far, be it in this part or the previous parts, that you can let me know. I'll surely, in the comment section, you can let me know. I'll surely reply to that. Okay, so now I'll be meeting you in the next video with the new part of it. So if you have understood the concepts, then make sure you like to the video and don't forget to subscribe because more videos are still on the way. Okay, thank you so much for watching.